Let's see, can you all hear me? Okay. Thanks for the introduction. We're going to shift gears a little bit from most of the talks that we've heard so far. Most of the talks we've heard today and most of the focus yesterday has been on the biochemical, or let's say enzymatic type conversion of biomass to fuels. What we're going to focus on today is more of the thermochemical and catalytic conversion of biomass. Right off the bat, I got to acknowledge my co-authors here, along with a bunch of students that aren't listed because I didn't really have them a lot of space. But Chris Roberts, currently the Dean of Engineering at Auburn, a lot of the experimental work that I'm going to show here came out of his lab. Dr. Steve Taylor, who talked earlier this morning, in his role as the director of the Auburn Center for Bioenergy and Bioproducts, a lot of the facilities that I'm going to talk about early on are under his purview. And we really have taken a team approach. There's a lot of folks here from Auburn that cover a variety of aspects, from the feedstock production, feedstock pre-processing, and also the conversion. And it's really a campus-wide activity. So if I can get this thing to work. This is kind of an overview of the biorefinery platforms that we have at Auburn. We have a lot of people working on the biochemical and enzymatic conversion routes as well, but I'm not going to focus on that today. Dr. Taylor talked earlier about the production of biomass, and we've heard other people talk about different types of pre-processing and pre-treatment, and we do have a lot of research going on there as well. What I'm going to focus on are two main aspects. I'm going to focus on a novel FischerTropsch process that's been studied in Chris Roberts' lab, and I hope I'm not stealing too much of Professor Davis's thunder for tomorrow, who's going to talk about FischerTropsch as well. But this one is run under different conditions than the work that is being done at University of Kentucky. So if I am stealing too much of the thunder, I do apologize in advance, and you can blame Professor Roberts on this. And then we're going to talk about a little bit some latest results we've done on mixed alcohol synthesis, very, very differently done than what Professor Holzapfel presented earlier this afternoon, where he went from the biochemical conversion route. We're going to do this from Syngas, so basically from gasification of biomass through mixed alcohol synthesis. So I wanted to say a few words about the Center for Bioenergy and Bioproducts before we get started, because it really has become the nexus on campus where we focus and coordinate a lot of these activities, and it also provides a framework in terms of larger scale equipment that we can use for more pilot scale / semi-industrial scale studies. So we've got a variety of different facilities there, and I'll go very quickly through them just to highlight along with some pictures. We have a very unique biomass fractionation facility that allows us to break down a variety of different biomass sources into its constituent parts. So you can get a reasonably pure cellulose stream, a pretty pure hemicellulose stream, and a reasonably pure lignin stream out of it. It's a countercurrent extrusion process that uses a alkali kind of solution. And the nice thing is, for the lignin in particular, you get a relatively low molecular weight lignin that is very amenable to further chemical processing if we wanted to go that route. But it's a very unique unit, and we've done this in collaboration with a company in Colorado called Pure Vision Technologies. This is their original process development unit that we bought and moved to Auburn. Kind of our centerpiece is our Gasification Lab. This is a major investment for a university, and we're looking at a large-scale fluidized bed gasifier. It's being constructed between Auburn and with GTI, the Gas Technology Institute in Chicago. We can operate this once it's finished. We're pressure testing and all that stuff at the moment. We hope to actually run the first test this semester. It can operate either air-blown or oxygen-blown, so we can play with the oxidation media as well. it can run at, if you look at the design pressure, fairly high pressures. The reason for that is that we wanted to have the ability to later on add the ability to gasify coal, or maybe co-process coal and biomass together. That's why if you look at the picture, the first one, you'll see that the gasifier is built a little bit off the ground. That's to have the ash removal to be added underneath if we were to go to the coal base. There's a variety of gas cleanup stages that can be swapped out. Along the way, we can test different sorbents and so on. And we have some downstream FischerTropsch reactors as well, where we can actually run on the real biomass. I will note, though, that the FT reactors that we currently have in there, not all of them are at the same scale as the gas that we're producing. So we have one that ConocoPhillips donated us that is somewhat smaller than the gas production of the gasifier, but we can run a slipstream off and produce some FT liquids from there. We also have a mobile gasifier, which is a more simple downdraft gasifier aimed at making electricity and heat. But it's a simple air-blown atmospheric conditions coupled with a 25 kilowatt electric genset on the back. Primarily is to illustrate that you can generate electricity and heat on a small scale. And this has been field deployed for the past almost 5 years. I believe it's up to something like 20,000 miles that the thing has been logged around the country. It's been everywhere from the West Coast to Washington. We also have a smaller scale gasifier that allows us to run more quick and dirty tests of different materials and conditions in order to prepare for the big trials that we're going to run on the big gasifier once we finish that. So basically what we're trying to do is make syngas. Syngas is a combination of carbon monoxide and hydrogen, and you can make this from any kind of carbon source, whether it's biomass, coal, or natural gas. The focus for this meeting and the focus of our center and the work that we've been doing has been on the biomass side. The beauty of the syngas, though, is when you have it in that form, there is a lot of different chemistries that you can be utilizing. The focus here that we're going to look at is on the FischerTropsch synthesis, and I'll mention briefly towards the end some work on higher alcohol synthesis. So what is the FischerTropsch process? Well, it's actually 100 years old. This was developed by two German scientists in the pre-Second World War days when Germany couldn't get a lot of petroleum and they had to use their coal resources to make liquid fuels for their war machine. I guess they weren't too sure about the outcome of the war. If you look at the picture of Professor Fischer there, dealing in a chemical laboratory with CO and hydrogen, and he's smoking a cigarette, I'm sure the OSHA people would have a lot of fun with that today. But the FT reaction is basically a surface catalyzed polymerization reaction that makes long-chain hydrocarbons from CO and hydrogen. You can use a variety of different catalysts, cobalt, iron, and ruthenium. Cobalt and iron are the two primary ones on industrial scale. Ruthenium is simply too expensive. This is what you usually get. Because you have a polymerization type reaction, you're going to generate a lot of different hydrocarbons in terms of their length. So you have a certain fraction that falls in the gasoline range, some that falls in the diesel range, some that fall in the jet fuel range, and some as waxes. And if you can look at the carbon number 1, you're going to generate a lot of methane as well. That's really not desirable. The methane part, making methane out of CO and hydrogen, that's not fun. We want to push it into the longer hydrocarbons that we can use either as chemicals or fuels. So what you often end up doing is very similar to what a refinery does. You have to do some upgrading. So in this case, if we run the FT reaction first, we're going to get a distribution that looks something like this. Then, in a single pass, you can add an additional catalyst bed where you're doing oligomerization. You take the light products and you recombine them to push them into the higher hydrocarbon range. Then you can add a hydrocrack and an isomerization step, which takes all the heavies and cracks them back to shorter hydrocarbons. And now, again, you're pushing the products into a higher content of the fuel range products. So that's basically what most FT processing is focused on. What I'm going to talk about is an alternative mode of operation for the Fischer-Tropsch reaction. What we're going to look at here is using supercritical phase conditions to run the FT reaction. Gas phase Fischer-Tropsch reactions have the benefit of having very, very fast transport properties. You can very quickly get the reacting molecules to the surface of the catalyst, and so you get a lot of efficiencies in terms of the transport. The problem is the gas is not a very good media for removing heat, and the Fischer-Tropsch reaction is exothermic, so you're generating a lot of heat, which is why you often end up with so much methane, because you get hot spots on the catalyst and that breaks down the long hydrocarbons. If you go to a liquid phase, then you have very, very good heat transfer capabilities and thermal management options, but you have relatively slow diffusion through the liquid phase, so that slows down the rates. And basically what you get if you go to a supercritical phase is the best of both worlds. You get vapor-like transport and liquid-like heat capacities. So what that means is, if you look on the left, normal gas phase FT, about 50% of your product are in the light hydrocarbon range. Well, that's not what we're interested in. We want to make gasoline and diesel range fuels, and maybe some waxes if we want to sell those as additional chemicals, but we want to primarily focus on fuels. If we move to supercritical phase, you'll see there's a distinct shift in that product distribution. You now have better than 75% of the product is in the fuel range. Another aspect that was mentioned in a couple of the earlier talks too, we may want to look at making co-products, higher value chemicals that may not have as big a volume as the fuels but have a higher value. One thing that's unique about the supercritical phase Fischer-Tropsch is that you make a lot of aldehydes and methyl ketones. You don't see that under gas phase conditions. So that's one of the unique aspects of this, this operational mode. So here's the experimental setup in Robert's lab that we're using to collect all the experimental data. I'll show you quickly some product distributions. I'm not going to spend a lot of time on that because they follow the general picture that I just showed you. Here is a product distribution for gas phase FT. At the top, you have just the first part pass through the bed. The second one is where you've added the upgrading, so now we've moved more material into the fuel range. One of the things that is also interesting when you compare the two modes of operation is the look at the CO conversion. The CO conversion under gas phase conditions is at the bottom here, and I don't know if this laser is working. It's probably hard to see. This is gas phase Fischer-Tropsch operation, both with and without the upgrading steps. All the way up here is where the supercritical phase conditions are. So you get a lot better conversion of your CO. Interestingly enough, when you look over here, you get a distinct drop in the methane selectivity. So much less methane is produced compared to the gas phase operation. All right, a couple more slides on this real quick. After you do the upgrading, you change the nature of the products a little bit. So you're generating some additional species that have positive fuel properties. For the supercritical phase, you can see the distinct shift in the properties. What's interesting here is not so much how much is being pushed into the fuel range, because the supercritical media already helps with that. The upgrading catalysts, in this case, actually add aromatics to a point where you're getting much closer to a petroleum-derived fuel. Okay. Now I'm going to really change gears from what we've heard the last 2 days, because none of the folks here are modeling people. I guess they're not used to handling the modeling part. So, I don't know, I guess I'll wing it. It's easier when you do the modeling anyway, because you don't have to deal with experimental error and stuff, you just change the conditions. What I was going to show you, luckily I didn't want you to actually read that particular slide, was just to illustrate that we have a very structured methodology of how to develop models for these different processes that are coming out of our consortia. And So I wasn't going to talk much about that, except I was going to show you the results of the modeling that we've done of Dr. Roberts' experimental results on the supercritical FT. I was also going to show you that it actually is economically much more attractive than, oh, they're showing my schedule here. Yeah, I know I'm on. So you're going to have to trust me when I tell you, hey, there you go. At least that one's on. So if you come around here, you can see that we have a framework for doing the modeling. There you go. All right, I can cut down on the stand-up now for a few minutes. Like I said, I didn't want you to have to read that, but basically we have a very structured way of evaluating and generating the performance data for the different experimental processes. One of the challenges is when you do these things in the lab, well, you're not getting industrial scale type data for energy consumption. Often you're not even measuring that. You're not worried about the calorimetry of the reactors. You're trying to focus on the chemistry. So what we've done is, in my group, we've developed a framework for how to generate performance metrics, both economic and environmental, for these types of processes, so that we can scale them to appropriate scales and actually compare them. Here's just a screenshot of one of those simulations. Most of the experimentalists frown on simulation, and you know, to some extent I understand that. These were actually based on a combination of open literature data that I'll show you in a second, and then the corresponding validation experiments that were done in Roberts' lab for both gas phase and for the supercritical phase FT. So in this particular case, we modeled the FT reactor using the Sasol's Argy reactor. 2,050 tubes, all the data is there. Since they're going to provide these to everybody, I'm not going to go through all the specs, but basically this is a well-established standard 900 barrels a day size plant that Sasol has published you know, all the data on. So for the supercritical phase FT, it looks very similar. And the only difference really is that you're not taking the lights and reforming those back to generate additional syngas. You use everything up to about C6 to generate the dense media that you're going to use to get into the supercritical region. Once we had the, excuse me, once we had the models, the next step in the optimization aspects is to look at doing process integration. There's a lot of potential for doing process integration in these types of processes. You start out with gasification that runs at very high temperature, and basically from the gasifier down to the products, you're going downwards in temperature. So there's a lot of latent heat that can be used. The FischerTropsch process itself is exothermic, so you can generate a lot of steam on those reactors. That's actually one of the ways that both Sasol and Centrolium are making their products profitable. It's because of all the steam they're generating. We used thermal pinch analysis and methods like that to generate the true energy requirements of the processes. You use that information to generate the corresponding heat exchanger networks to recover all the waste heats and so on. And then at the end of it, you can then start comparing the different types of processes without having to build it. That's really the key benefit of doing the simulation work. But here in this case, the conclusion is, even though you're running at significantly higher pressure to get into the supercritical region, the supercritical FTS, it does cost about 20% more in terms of the energy consumption, but you produce about 50% more fuel. So that makes it very, very attractive in that respect. We also did a comparison between the Argy reactor setup and what the equivalent reactor would be on a capital cost basis. And there's a slight difference in cost there that favors the supercritical phase as well, because the reactor would be a lot simpler. But they're at least very comparable, but the fuel production increase makes a big difference. And this is for the same syngas feed, I should note. So I had to do a little song and dance, so I'm going to try to recover the last few seconds here. A little bit on higher alcohol synthesis in a different way than Professor Holzapfel presented. It's a very, very similar reaction to the FischerTropsch reaction. You're reacting CO and hydrogen to generate alcohols. You can, on one particular catalyst, you can make very, very efficient methanol production, but you can use other catalysts and get a distribution of higher alcohols. You're also making hydrocarbons, just like you would in the FT process. The difference between the two is that in the FT process, you want to maximize the hydrocarbons and minimize the oxygenates, and in mixed alcohol synthesis, it's the opposite. So what we're trying to do here is maximize the alcohol production. And you need, in most of these reactions, you need a 2-to-1 ratio of hydrogen to CO to get these types of longer chain molecules. Now, if you look at the comparison between conventional gas phase alcohol synthesis and supercritical phase, you'll see a distinct shift again in terms of the productivity of alcohols under the supercritical conditions. And you also see a distinct suppression of the paraffin production. Then the question is, how much of this hexane phase do we have to add? We looked at a variety of different hexane to syngas ratio, and you can see if you're moving from having no hexane in there, which is what we use to model the dense media in the lab, you get a certain product distribution that it's at the very front of this curve. Let's see if this works. As you're adding more of this dense media, you can see a distinct increase in the production of alcohols. Now, what's even more interesting is when you look at the effect of the hydrogen-CO ratio. In gas phase, if you move from a ratio of 1 to 2, you see a distinct increase in alcohol production, which is what is expected. However, under supercritical phase conditions, you'll notice that the scale here is reversed. Otherwise, you wouldn't be able to see anything because you actually get the highest production at a hydrogen-CO ratio of 1. If that had been at the front, it would have covered up the other lines. But that is actually very, very important in the context of this meeting, because when you gasify biomass, you get something that's very close to a 1-to-1 ratio of hydrogen and CO. Biomass and coal are very hydrogen deficient. That's why most FT processes on industrial scale are based on either water gas shifting the gas to getting the right hydrogen content, or you run it on natural gas, which has a much higher hydrogen to CO ratio. But this is an interesting result. It's very recent, so we don't have much more than that. That just came out of Robert's lab maybe a month and a half ago. But this makes the potential for making alcohols out of biomass through the thermochemical route a very attractive option, because you don't have to do so much shifting of the gas. It'll also allow for a higher carbon utilization by not using the carbon to turn it into CO2 from water gas shift. So, quick summary, I didn't talk much about the fractionation because I couldn't cover that in the amount of time I had. One of the things that is unique about it, it allows you to target different processing routes for each of the constituent species that might be interesting in the future. Doing FischerTropsch and alcohol synthesis under these supercritical phase conditions gives you a significant increase in the fuel range products. You get a better carbon utilization as a result of that because you're not wasting it making methane. An interesting aspect is the co-production of aldehydes and methyl ketones. And specifically, the higher alcohol synthesis is interesting because it's favored at lower hydrogen-CO ratios. The modeling and optimization, even though we had a computer glitch, which usually doesn't happen in my lab, it does allow a systems-level analysis of the different processes, which is particularly important when you got a lot of different experimental researchers working together, trying to bridge the gaps between the different scales they're working on and the different types of processes they're dealing with. So at the end, a few acknowledgments. This work has been funded by a lot of different agencies, the National Science Foundation, the Department of Energy, Department of Defense, the EPA, USDA, NEFA. Dr. Riles earlier today talked about some of the work within IBIS. This is certainly a part of that as well. And our IGERT is drawing a lot of these results as well. So with that, I'd like to thank you for your attention and take any questions you might have.
We have some questions? I was wondering, when you calculate the selectivity for hydrocarbons, did you calculate did you count the carbon dioxide productivity?
No, this is on a carbon dioxide-free basis. This is the hydrocarbon selectivity. This is based on GC mass spec of the liquid products, and so all we're focusing on there are the hydrocarbons.
Yeah, I was worried about the carbon dioxide produced by your supercritical conditions, because you can see that you had a higher production rate when it's 1-to-1 ratio, which means that you must produce a lot of carbon dioxide, otherwise the reaction cannot close. You can see the production for the hydrocarbons or the alcohols need 1-to-2 ratio, not 1-to-1 ratio. So, which means you must produce the carbon dioxide to finish the Fischer-Tropsch reactions.
Well, there's a little bit of a difference there. For the FT reaction, you're not moving to 1-to-1. That was for higher alcohol synthesis. So that's one aspect. And since the comparison there is based on the same set of conditions, the same syngas rate, and you're looking only at the product yield, then it really doesn't matter where everything else went. You're looking at what the conversion and yield is in a single pass, and in that case, it's still outperforming the conventional setup. For the FT reaction, you're running closer to a 1.8 to 2, even under supercritical phase conditions. And if I could bring up that slide, the CO2 selectivity under those conditions are much, much lower for the supercritical phase than it is for the gas phase. Whoever is in the control in the back there, if I have control over it, I can bring it up. Oh, there it is. If you can bring it up on the screen, excuse me. Over here on the right, you have at the top here the CO2 selectivity as a function of time on stream. The focus here was in terms of the stability of the catalyst and the operation, so we're looking at a certain amount of time. But you can see there's a distinct difference still in the gas phase CO2 selectivity over the supercritical phase CO2 selectivity. So I hope that answered your question.
Okay.
Oh. Other question?
Yes, hello, Andrew Lepore from the University of Tennessee, over here on your right.
Oh, there you go. I'm sorry. I'm working on my tan up here.
That's okay. My first question was, do you use that cobalt catalyst in your supercritical FischerTropsch synthesis? And the second one was, you see aldehydes, ketones, cycloparaffins. Have you looked at maybe doing any mechanistic studies to see what's going on, any computer-based modeling?
Okay. On the first question, in Robert's lab, they have run it with both cobalt and iron and different types of promoters, potassium and others. We've done the results for both. In terms of the mechanistic modeling, I haven't done any of that. One of the things that they have done in Robert's lab is they have studied the time-resolved product analysis, and the aldehydes and ketones are suspected, probably even hypothesized to be in the primary products of the reaction, and that is what actually gets converted to the olefins and paraffins. And so the mechanism hasn't been discussed or published yet, but it is what they're thinking based on what they're seeing in the time-resolved studies. It would appear that the oxygenates are actually the primary products, which then reabsorb on the catalyst and get hydrogenated to make the olefins and paraffins. The aromatics come primarily in the upgrading step. They've pushed the latest results that I saw and get up to about 30% aromatics in the product in a single pass after the FT process, which is actually too much for what you want for fuels. You want probably about 15 to 18 is, I believe, what the jet fuel standards are for elastomer swelling and stuff like that. but you can generate a lot of aromatics in that. Also cycloparaffins.
Thank you, Mark. I want to remind everyone, this isn't the last session today. There's one at 7 o'clock.